Hello everyone. So in this second lecture we will be seeing how a resistor will be behaving when excited by an AC voltage source. In the last lecture we dealt with the introduction of alternating currents, and we saw what are the standards of single phase supply in India, and just we discussed a general outline of what RMS values are, and we also learned why AC is important. So in this lecture, we deal with the first analytical topic of this chapter, that is the when resistor is excited by an AC source. So now let's focus on this circuit. Suppose this is a resistor R and it is excited by an AC voltage source, the alternating voltage source, sinusoidal voltage source. So this waveform looks like this. Suppose if I'm taking omega t axis as the x-axis, and this is the function of time, your voltage, which is Vm sine omega t. Okay, this is a sinusoidal curve. This is going on. Now, if Vm was not there, if we say a general sine wave, say sine t or sine omega t, just only one is here, nothing is here, only sine omega t is there. Then we know the maximum minimum values of sine function is +1 and -1. +1 and -1. If we multiply this sine function by some constant, say Vm, then these maximum minimum values will also be multiplied. If it is +1, then it will become equal to whatever the thing is multiplied here. Suppose Vm is multiplied here, so the maximum value will be Vm. So this will be plus Vm, and instead of -1, this value will be minus Vm. So this is the case. This is your source. Okay. This is the source which we are giving here. This is a graphical manner. I am taking omega t as a reference axis. So these time axis is converted into angles. So this will be 0. This is pi by 2. Okay. This is pi, 3 pi by 2, and this is 2 pi. So like that. I converted this angle into angles by multiplying it by omega. So omega you need to know, which is here angular frequency. Angular frequency, which is also equal to 2 pi f. Okay, and this frequency is the frequency of this supply. Like in the previous lecture we discussed that 220 volt 50 hertz supply, so that 50 hertz is the f, that same f. Okay, this is the frequency of the supply we are talking about. So this is the angular frequency. Obviously the current flowing is I. Now I have marked this direction. Obviously current is positive. I will consider positive if it is according to my convention, and I will say it as negative if it is against my noted convention. So whatever that is the case. So let us discuss now. If you apply Kirchhoff's voltage law or Ohm's law here, by Ohm's law you can write easily here that I will simply write Vt this V. Okay, so it is easy to note. So capital V means this Vt only, function of time. Okay, it's voltage. So V is equal to this I into R. This you know. Okay, by Ohm's law. Now I is equal to, we need to find I. We know V is equal to Vm sine omega t, Vm sine of omega t upon this R. Now if I club this Vm by R together, I can write it as, if I am taking this Vm by R as say Im, this is the case where Im is equal to Vm by R. Okay. So observe the expression of current we obtained here. It is also a sinusoidal wave, just like the source. We have similar kind of a waveform as the current. And you notice that this Im is V maximum by R. Obviously, this V maximum is divided by something. Obviously, this value of Im is less than this Vm. Im is less than Vm. You can understand from here. And you observe another thing. as this angle and this angle, both these angle are same. Whatever time you take for any value of time, value of this capital V and value of this capital I is in phase, because both angles are same. This angle and this angle are same. So these waveforms will look like this. If I want to draw these waveforms, suppose I say this is the waveform for V, okay, like that it is going on. This is omega t. If I say this is the waveform for V and this is the maximum value of Vm, obviously by this I can say Im is less than Vm, and as the phase is same, both have same angles, so both, if this graph begins from here, current graph will also, the 0 point will be here, and when this voltage graph reaches maximum, current will also be reaching maximum, like this. Both will be in phase. Okay, like you have seen in the Republic Day parade that all the people in those parade, their hands and feet move together. Their motion coincide. So like that, I and V are in phase here, but Im is less than Vm, so its maximum will be less than this Vm, suppose here. So this waveform will be like this. This is also sinusoidal, but the maximum will be less than the voltage. So this is the kind of voltage and current waveforms you will be getting in this resistive circuit. So this waveform, this is the behavior of current. If you excite this by an AC source, then the current will also be the same behavior. It is also I. It is also a sinusoidal wave. This is clear. Now we need to see. Let us talk about power for a while. Okay, if I say as a general expression, P is equal to I square R. Okay, so here I can write I have calculated. So I am sine omega t whole square into R. Now, what kind of power is it giving? Here T is there. Suppose in DC, if I talk, in DC I say let us denote DC power in small letters. P is equal to VI, we say there, or we say I square R. Okay. Here the power, there is no such time is here, as this power is dependent on time. Whatever value of time you put here, you will get a corresponding value of power. Such power will be instantaneous power. You need to understand from here. Instantaneous power. Okay, whatever. So this instantaneous power means power at a certain time. Okay, power at a certain time. For a value of t, you will get a value of time at a certain time. People get confused in these terms, so you need to understand that at a certain time, at a certain point of time, if we point the power, then that power is instantaneous power. Okay. Now we need a similar kind of expression as in DC. This is DC in DC. So in our analysis, we define power in AC as average power. In AC circuits, if anybody tells you find the power or find the power in this AC circuit, generally he is not talking about instantaneous power. He is talking about a term known as average power. What power? Average power. He is talking about average power, which is denoted by a bar over the letter, generally P average, or you can sometimes write in the subscript like this, whatever. Let's go by this notation as of now. So average power is the power in a cycle. As you know, alternating current is an AC current, so there will be time period. So we will be in average power, we talk about power in a particular cycle. So if we say power equal to, say, Im sine omega t whole square into R, then average power is what? Since Im square I can take out because it is a constant value and R is also constant. So average of this sine square of omega t term. This is the notation for average. Okay, these brackets are notation of average. So this average value of this over a cycle. Okay, over a complete cycle. Now you can calculate this. I can write Im square into R, and sine square omega t you can write as no sine square theta, you know formula, 1 minus cos 2 theta upon 2. So if you use here, that will be 1 minus cos 2 omega t by 2 average value. If you write in this manner, you take half separate and cos 2 omega t by 2. Okay. What you can infer from here? This is constant, so this will be outside of the average calculation, 1 by 2. And you are left with this term, okay, cos 2 omega t by 2, whatever it is. Now, average, if we take average, what is average? If I say sine value or cosine function is like this, okay. So if I say this is going to be as one cycle, this is all the cycle of cosine is also 2 pi. And if I say sine function cycle is also 2 pi. And what is average? Average is nothing but area under this curve. Area under this curve is what? Integration of these curves. Okay, integration of, say, if it is omega t, sine omega t. If this is omega t, this is cos, so cos omega t. Okay, area and divided by the time period, that is 1 by 2 pi. Whatever, if you integrate this or if you calculate the area of this curve in a complete cycle, this is positive will be cancelled by this negative. This positive area will be cancelled by negative area, and thus also this plus area is equal to positive area will be equal to negative area, and thus ultimately the average you will be getting as 0. This average is 0. Okay, so average of this is 0, so you will only be left with half here. So that is why the power expression you will be getting it as Im square R by 2, because this is 0. Okay, this complete, actually this calculation, this whole calculation is 1 minus cos 2 omega 2 by 2. This whole calculation will give you half, so you don't need to write this, it will be more confusing. So this is the thing, you find the average of this average is 0, you are left with only half anywhere, so that's why the average value of power is Im square R. Now let us, you know that in DC P is equal to I square R. Now I told you that the significance of the RMS values is that to make the DC and AC equivalent, the analysis of AC equivalent to that of a DC circuit. So if you compare, R is common in both the expression, this I square and Im square by 2 are equivalent. So if I write this, suppose I consider this as Irms square, Im square by 2. Why? Because according to my analogy, what I said, that the RMS values are the equivalent values of voltages and current, which are equivalent to the DC. So if I say Irms square equal to Im square by 2, that means Irms is under root if I take Im by root 2. Meaning is this power expression reduced down to IRMS square R. Okay, this IRMS. So this becomes this. So now you can see that these both circuits, this is AC average power and this DC. In these both, now this circuit this expressions have become equivalent. Whatever we talk current in DC circuits, that is RMS value in AC. So this becomes P equal to I square RMS. Similarly, I can write in terms of voltages also. I can also write this as Vm sine omega t. Okay, Vm sine omega t whole square upon R. So if you calculate in this manner, then you will be getting average power. Similar calculation, if you do like this, you will get it as V RMS square by R. Okay, and where V RMS is equal to Vm by root 2. The similar you can take voltages. Okay, voltage expression. Similarly, the sine square, the same function will be, their average value will be again half. So this half will come in here. Okay, so you will get Vm by root 2 as the RMS value, and your power will be, you will be getting as Vm square by 2R. Okay, so that will be the thing. Anyways, this is the expression. Now let us, I have calculated IRMS with an analytical method, with an analogy. I have, by definition, I have found out the value of IRMS and VRMS here. I will also derive it mathematically later on. For first, let us first see the graphs, okay, so that we can have a better understanding. So we will see the graphs for power in this circuit. Let us see graphs. Okay, graph of AC power, all in resistive circuit. We are dealing with the resistive circuit. Okay, that is only a resistance is connected, resistance is excited. Now let us see the curve. Okay, let us now, if I take I graph, okay, this is I, this is omega t. The graph is sinusoidal in nature. We have already found out the current in this resistive circuit. Okay, this is pi, this is 2 pi. Fine. Now power I, by the expression you have seen that power is this I times square R. That is also Im sine omega t whole square into R. Now again Im square R sine square of omega t. Now observe this expression. Okay, power expression. Observe this expression. This is square of this sine. This is square of this. If you do square of this waveform, what will you be getting? See, first of all, you need to understand the power is not zero in resistive circuit. Okay, how? Because if you see this graph, you will understand better. This is omega t, and this is the graph of power I am telling you. Sine square of omega t. Okay, this maximum value is Im, and maximum value of sine function is 1. 1 square is 1, but so maximum value will be Im square R. But the graph will be kind of this manner. Up to 0 to pi I am drawing. So 0 to pi it is positive, positive square is positive, the graph will be like this. Let us see from pi to 2 pi, this is important. The graph is negative here. But if I square, because this is in power, the graph is squared. So this becomes positive again. So graph will be in the positive direction only. Again, the cycle begins from here. Again, it will be like this. And it will be continuous. So you can observe easily that pi is the time period of this waveform. And as the maximum value you can calculate if this is maximum value is always 1, so Im square R can be the maximum instantaneous power at this time. The maximum power is occurring, which is pi by 2. So in multiples of this, again 3 pi by 2 will be having Im square R. So you need to understand the main thing is that this graph is not becoming negative. This graph is not becoming negative. Not becoming negative. Okay. Not becoming negative. So that is why what I'm telling is you will have a certain value of average power. So say here, somewhere here average power will be. So if you calculate area under this curve, or you calculate the average value, that will hold a value. It will not be 0, because this kind of a waveform is observing power when excited with a AC source or resistor. Okay. So this is important. Now let us see the mathematical derivation for RMS values. See, somebody asks you a question, derive RMS value. Okay, so RMS current I am telling. Now we will go in the mathematical part. Now previously I have explained you so that conceptually you can understand. So suppose I am taking again the same waveform. The current was like that in the resistor circuit we saw. So it was like that. This is pi, this is 2 pi. This value is Im. Okay. This kind of a graph you are getting in the current. Now we need to find the RMS current. RMS current is nothing but root mean square. Always remember, when we find RMS, when we derive the expression for RMS current, this is a derivation. Okay. Derivation of RMS current I am talking about here. Suppose in exams somebody asks. You need to understand that the order, you need to follow the reverse order of this RMS word while deriving the expression. Like this, you need to go this in this manner, right to left. First you will square, then you will mean it or average, and then under root. Okay, how this is being done? You need to find RMS of current. No, so you consider this graph. This is the current flowing in that resistive circuit. That is I is equal to Im sine of omega t. We need to square this. Okay, so I will write the I RMS expression as square. First of all, we will square. So what we will square? This complete current we will square. Sine omega t whole square. Done. We need to find mean. Okay, mean means in statistics. In statistics, you might have seen the mean or the arithmetic mean. You used to calculate AM or arithmetic mean. That was the discrete data. That was not continuous time domain data. So that there you explained it as summation of all observations divided by number of observations. That was a formula. Similarly, average is also the same concept here, but this is continuous signal, continuous time domain signal. There are no breaks observed in the graph. It is continuous time. So for continuous signal, this summation is nothing but the integration. So integration of the whole graph divided by the time period. That is the area upon this time period will give you the average value. So here, if I am taking omega t as a reference, I will take the integration in terms of limits of omega t only. That is in one cycle. What is one cycle? Integrate. We will integrate this in one cycle. What is one cycle of this? It begins from 0 up till 2 pi is one cycle. After that the graph repeats. So this is one time period. Okay, this is one time period which is equal to 2 pi in omega t terms. Since I am differentiating with respect, I am integrating with respect to omega t. So I will be writing the limits in the same format. So 0 to 2 pi is the one cycle, and the duration time period is 2 pi. This is now the average. This step is done. This step is done. Finally, is what we need to take the under Okay, making this under root again, I will use power minus half. Okay, so you can write this expression as, obviously this Im square will come outside. Okay, upon 2 pi, and I can write this sine square omega t as I have used it earlier, so you can understand now. 1 minus cos 2 omega t upon 2 integration 0 to 2 pi d omega t. Okay, this is what, and obviously this is under root. Okay, so now if I integrate this, let us write step by step so that you can understand it better. This will be 1 by 2 here minus cos 2 omega t upon 2, and this complete is integrated. Okay, and this whole power is that is the under. So if you see Im square by 2 pi, half, if you integrate this, this will be omega t by 2, and the limits are from 0 to 2 pi. Okay, minus integration of 0 to 2 pi, this cos 2 omega t by 2 d omega t, and this whole is under root. Now see this expression here. See this expression here. This is again the same thing. I told you that over a complete cycle, summation of a sine or cosine function is always 0. Okay. So you need to understand this complete. After this, it will be repeating. So complete over, if I say one cycle, the cosine function, the area is 0, and this is integrated over one cycle 2 pi, and this is a cosine function, so this will be reduced down to 0. So ultimately we will be left with Im by 2 pi, and if I put the limits, you will be getting is 2 pi by 2 whole under root. So you will be getting it as 2 will be cancelled, pi will be cancelled. You will be getting, obviously this, I forgot, this is square. So this will be under root if I take Im by root 2. So this was the expression for RMS. You get again Im by root 2. So somebody says derive it mathematically, you can show them yes, by this you can go. Similarly, if he asks for voltage, you can consider voltage waveform and derive in a similar manner. Okay, so this is what you need to understand. Obviously, one more relation is important here. I told you in the yesterday's class, observe this relation, IRMS equal to Im by root 2. It means Im is IRMS root 2, or Vm also equal to Vrms root 2. Yesterday I told you that supply in India, sinusoidal you are receiving in single phase AC supply at homes. There, this was the Vm. So I told you 220 volt 50 hertz is the supply in India. So this was RMS. Now suppose I ask you to what peak voltage you are receiving in home. So you can easily find by this expression, which is maximum value, this value you are getting as RMS 220 multiplied under root 2, which will be, if you calculate 1.41 under root is, so around 311 volts you will be getting. So the maximum value is 311 volts which you are receiving at home, and a true of minus 311 volt. So don't confuse. This is the RMS value. Okay, this kind of a expression. So you need to remember this expression. Im by root 2, Vrms equal to Vm by root 2. These are the RMS expression. These need you need to remember. Again, if I talk about the average current and average power value, the average current, if I say, let us talk about average current. I am considering this whole cycle, okay? Again, if I have this graph, this is omega d. This is, you are having a graph of the current. This is I. This is obviously the maximum value Im. This is 0, I, 2, I. Okay. Now, average, obviously, I told you as it is, average value of a sine or cosine function. This is Im equal to sine omega t. Or even if it is a cosine, Im cos omega t, the average is 0. You can calculate average if you need to find out. You can also integrate this. Im sine omega t d omega t. Okay, integration respect with limits 2 to pi. So time periods is 1 by 2 pi. So if you find this, sine omega t will become 0. So average value will be 0. Now there is a concept. Similarly, for voltage, if you calculate the average also, you will get 0. Now these are both when we talk about full cycle average. Okay, full cycle average. These are full cycle average. When we consider, we are doing with this limit in the limit of full cycle. There is also a concept of half cycle averages. Okay, when we find the average within the half cycle, this is the full cycle up to 2 pi, half of this is pi. So there is a concept, if somebody asks what is the half cycle average, so we will now see half cycle. Now in half cycle, this I average half, I say, half average will be, the time period will be reduced to this, and it will be Im sine of omega t d omega t. If you evaluate this, Im will come outside, pi will be here, and sine omega t integration is minus cos of omega t, limits within 0 to pi. Okay, so this will be Im 1 pi minus of cos of pi. Okay, minus, again this is minus, so it will become plus cos of 0. Okay, so you know this cos pi is minus 1, so minus 1, this will be plus 1, and cos 0 is 1. So 1 plus 1, this becomes 2, and so you will be getting it as pi. So this becomes 1, this becomes 1. So this is 2 Im by pi. So if you are finding an average for half cycle, okay, then you are not getting it as 0. You are getting like this. Similarly, if we are asking about voltage, you must find, this is your homework, you find the V average half cycle. Okay, you will get the same expression 2 Vm by pi, but this is important. The half cycle average is not 0. The half cycle average is 2 Im by pi, but the full cycle average is 0. So this is the thing I told you, and I have also told you the expression for power, which was, this is the half cycle. Okay, and this is where I calculated the RMS. I also calculated the averages for you, and this is the power. Okay, and this is the power expression. Now also here you can write power is IRMS square. Also power as you can also write similarly power as Vrms square by R. Okay. So ultimately, if you see R in this circuit, okay, in the circuit I drawn, if Irms R is the drop, okay, so Irms R will be this voltage Virms, okay. Yes, you must understand, because you can write by this, you can write also the power expression as P is equal to R becomes Vrms by Irms. So this can be also written as Vrms into Irms. These are all just general expression. I wrote this expression so that you can compare with the DC. And DC, if I denote by small, P is equal to V into I, then in AC, average power is Vrms into Irms. In DC, if I say P equal to I square R, in AC, I say P average power is I RMS square R. Similarly, if I say P equal to V square R by R in DC, I say V RMS square by R in AC. So this is the significance of RMS value to make this analysis equivalent. So this is what we are seeing, those values, RMS values, average values. Now let us talk a little bit about phasor diagrams, just an introduction, because here we will be dealing with the phase angles. Phasor diagrams. Now, as you have seen that there was no phase difference between V and I in resistive circuit. The expression for current was Im sin omega t, and for V it was Vm sin omega t. There was no phase difference, both the phase angles were same. Phase angles were same with respect to time, and that is why there was no phase difference. But phasor diagram give you a very good indication of how the phase difference is varying. Okay. So phasor actually is, I need to understand what is phasor first. So phasor is nothing but a line or a vector, you can say a line which is rotating at an angle of, say, omega, at a speed of omega, which is the angular frequency. Okay, suppose like this. This is this tip. This magnitude will be the peak. Magnitude will be the peak. Peak is determined by the magnitude of this vector. So, and this will rotate at an frequency of omega. So let us go by the definition of your text as is described in the textbook. He's saying that a phasor is a vector which rotates about the origin with angular speed omega. So let me explain you what he's meaning by this explanation. So according to the definition, phasor is a vector, let us better a vector which rotates about origin in anti-clockwise direction. Okay, depending on the phase angle, that is a different thing. A vector which rotates about origin with an angular speed omega, which is your supply, okay, frequencies. angular speed omega. This is known as a phasor. That is, suppose this is the origin point, and if I am saying this is a phasor, this will be rotating as value of omega with the speed of omega, whatever frequency, and this is dependent on frequency. So higher the frequency, higher this omega will be, and how very fast it will be rotating. So this phasor will be rotating in anti-clockwise direction. This is what phasor is. And always the magnitude of this, the tip of this is determining the peak. Okay. And for a resistive circuit, let us do the phasor. This phasor can be for separate quantities, say voltages, current. Okay, if I say, since I am sine omega t, I say current as, I define current voltage. Suppose I take voltage as like this. In resistive circuit, this is the voltage. And if I want to draw the curve, this is omega t axis. Okay, these are separate. And at a particular time t1, say this is the angle subtended by V phasor. This is a phasor. Angle is always anti-clockwise. Okay, we take angle anti-clockwise. So this tip is nothing but that value of that phasor at this particular moment. Say, suppose like that. The tip will be when this phasor becomes maximum. Suppose this is the case. Somewhere here, these are. Okay, this is omega t1, and this graph is like that. Suppose sinusoidal it is going, and at this value, this phasor will come rotate. It will rotate again. It will be rotating with an speed of omega. It will come here at this condition. Okay, so these are nothing but a way to determine the phase relationship. Suppose in resistive circuit, the voltage and current phasors will be like this. If I say voltage is like this, the current phasor also will be coinciding with this, because there is no phase difference. Both angle is same. This also subtends omega t. This also subtends omega t, suppose. So both will be in phase, and these will be rotating together. They will be rotating together. If there was phase difference, suppose I say some phase difference was observed, then these V might be here, I might be here. They might have some phase difference, and then they may be rotating. By maintaining this phase difference, they might be rotating within a speed of omega. This is the significance of phasor, that it represents phase difference very nicely. So V and I coinciding, that means you need in future also, if you say this kind, see this kind of phasors, V here, I here, any kind, V and I, these both coinciding, it means this is a resistive behavior. Okay, resistance, because there is no phase difference in a resistive circuit, that we have already seen earlier. When we talk about inductive and capacitive circuits, we will not be observing this kind of a behavior, because there will be some phase difference between voltages and current. All in all, you need to understand what phasor diagrams are. These are nothing but phasor diagrams. If I take these are nothing but these are phasor diagrams only. This is phasor diagram. Okay, and this is the significance of phasor diagrams. They will be important in our analysis. Okay, we can take any one value as reference. We will see more about phasors. We will understand it better when we will be dealing with the inductive circuit. So let's conclude for today's class, and let us see what we have learned important things today. So we discussed resistive circuit excited by AC source. Okay, so in this, what we observed, first of all, we saw that we found the expression for IRMS, VRMS, okay, and we also find the expression for half cycle averages, full cycle averages. And the thing we observed is that current and voltage are in same phase. Current and voltages have same phase, there is no phase difference. Okay? There is no phase difference. No phase difference. Phase difference is 0. That's also true. Phase difference equal to 0. Moreover, full cycle average values of voltages and current are 0. Okay. Also, we saw some important expressions. IRMS is nothing but maximum value for a sinusoidal wave, maximum value by root 2 times. Similar is the case with VRMS, which is Vm by root 2. We discussed the average power in AC circuit, which is VRMS to IRMS, or you can say IRMS square R, or you can say VRMS square by R. We saw the graph of this power expression. We saw what is the difference between instantaneous power and this average power. And generally, when you need to remember this again and again in numericals also, if only power is not specifying which power, instantaneous power or average power, you need to take it as average power. By default, if he is using the term power in case of AC circuit, it means it is average power. So remember these expressions, these are important. And also one more important point, the averages were 0, full cycle, when we talk about full cycle averages were 0, but when we talk about half cycle averages, half cycle what we got, I average for half cycle, we got what we got, 2Im by pi. Okay. Or if it is voltage, it is 2Vm by pi. So that is all for today's class. We will see more about how an inductive circuit, how a coil and inductance will behave when excited with an AC source, and we will be getting to understand this phasors more easily when we talk about the inductive circuit. So thank you. Let us continue in the next class.